This is part 2 of proof by contradiction. So our strategy for proof by contradiction is to assume that the statement we wish to prove is false, and then show that this assumption leads to a conclusion that is false, or a contradiction. So before we start with some proofs, just a definition. A natural number is prime if it has exactly two distinct divisors. So distinct means different or not equal to one another. For example, 3 is prime because it has exactly two distinct divisors. 1 divides 3 and 3 divides 3, and those are the only two divisors of 3. In general, if P is prime, then it has only two distinct divisors, and those divisors are 1 and itself, dividing P. A natural number is composite if it has more than two distinct divisors. So, for example, 4 is composite because 4 has 3 different divisors. 1 divides 4, 2 divides 4, and 4 divides 4. So it has more than two distinct divisors. And note that 1 is neither prime nor composite. So 1 is neither prime nor composite because it doesn't have exactly two distinct divisors. It only has one divisor itself. Every other natural numbers are 1, 2, 3, etc., all the positive integers. Every other natural number is either prime or composite. One thing to notice here is that if n is composite, so if n is composite, it must have more than two distinct divisors, and at least one of its divisors must be a prime number. So if n is composite, it has some prime divisor, because if not, we could break it down, and eventually we will come down to a divisor that is has at most two distinct divisors itself, some divisor that is prime. So we now want to prove a theorem. There are infinitely many prime numbers. This is the first time that we are proving what I would call a theorem in this course. Everything else we have proven has been a proposition so far, but this is a pretty exciting theorem, something that is not necessarily totally obvious. There are infinitely many prime numbers, not a finite number of them. So let's do this proof by contradiction. So proof. Well, if there are not infinitely many prime numbers, then there must be finitely many. So suppose for contradiction that there are only finitely many prime numbers. So if there are only finitely many prime numbers, then we can list this finite set. So we can list all finitely many prime numbers in order. And we don't know how many there are, but let's just say there are n of them. So we have P1, P2, P3, ... up to Pn. And the list ends at Pn because these are all primes listed in order, where Pn is the largest prime. So it may be that P1 is 2, and P2 is 3, and P3 is 5, and so on. And we know what those are. But whatever the largest prime is, we're not saying what it is. We're just saying there is a largest prime because there are finitely many prime numbers. Okay, let's now consider P1 times P2 times P3 times ... times Pn plus 1. So let's consider that number, and let's call it the number a. So a is equal to p1 times p2 times p3 dot 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 up to pn, the product of all finitely many primes plus 1. Observe, so we're considering that, observe that a is greater than pn, and since pn is the largest prime, so a is therefore composite. Every natural number larger than 1 is either prime or composite. And so a has at least one prime divisor. And we have listed all of the primes above, so that must be equal to pk for some k, where 1 is less than or equal to k, which is less than or equal to n. So in other words, it was one of the prime numbers that we had up above. Okay, so if that's the case, let's now see that a must be equal to, so a must be equal to pk times t, where t is an integer, because pk divides a, and therefore it's the case that a is equal to pk times t is equal to, well, a by definition was p1 times p2 times p3 times dot 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 times pk is in there somewhere times dot 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 pn plus 1. And we can divide both sides of this equation, or divide this equation by pk. So if we do that, we arrive at pk times t over pk is equal to p1 times p2 times dot 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 pk times dot 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 pn over p sub k plus 1 over p sub k. And now we have arrived at, this implies that t, so we can obviously cross out, and we're left with t on the left, is equal to, well, pk cancels out with the pk in that fraction up at the top, so p1 times p2 times dot 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 pk minus 1 was the one before it, pk plus 1 is the prime after it, times dot 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 pn plus 1 over p sub k, that kth prime. And we could continue, and let's isolate 1 over pk by itself. So t minus p1, p2, dot, 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 pn is equal to 1 over p sub k. And now we see where our contradiction is going to arrive. Our contradiction is that the left-hand side is an integer and the right-hand side is not. So observe that t minus p1 times p2 times pn is an integer, while 1 over pk is not in the integers, since pk is prime, meaning pk is in the natural numbers, and pk must be larger than 1. So we have an integer equal to a non-integer, which is a contradiction. So we have assumed that there were infinitely many primes and come up with something that is clearly false, a contradiction. Therefore, if there are not finitely many primes, there must be infinitely many primes. So we have just proven that there are infinitely many prime numbers. Okay, so we've proven something pretty exciting, that there are infinitely many prime numbers, and this might be out of the scope of something that I'd expect you to do for homework, but it is understandable, I think. The proof is understandable given the background we've had so far in this course. And I'd encourage you to look back at that proof and make sure that you understand the steps of why it works, because that is a really fundamental theorem. And I think it's nice to feel like you fully understand it. Okay, so let's talk about another theorem, the fundamental theorem of arithmetic. Any integer greater than 1 can be written uniquely as a prime or as a product of primes. Uniquely means in exactly one way or only one way. So unique is a special word in math, meaning exactly one way. So let's just see this for a few integers, any integer greater than 1. Let's think about, like, say, for example, n equals 7. Well, that is a prime, so it can be written uniquely as a prime number, whereas n equals 12. Well, 12 is 3 times 4. That's not yet a product of primes. 12 is 3 times 2 times 2. Okay, there we go. N equals 12 has been written uniquely as a product of primes. This uniqueness is, of course, up to order in which multiplication occurs. This could also be written as 2 times 3 times 2 times 2 times 3. But these are considered the same because multiplication is commutative. So there's only one product of primes that any number could be written as either a product of primes or as a prime itself. This theorem we are not going to prove right now. You will either see the proof of this theorem in the continuation of this course in proof 2 and or in number theory. So if you take either of these courses, you would see a proof of the fundamental theorem of arithmetic. For now, we are going to assume that the fundamental theorem of arithmetic is true. We're going to take it as an assumption for now. We're going to use it to prove this other theorem that will be useful for some other proofs that we do within the course. So theorem, suppose n is an integer and p is prime, then p divides n squared if and only if p divides n. Okay, so let's do a proof for this theorem, and we're going to do this in cases. So case 1, suppose that the absolute value of n is greater than 1. So in this case, if n is greater than 1, then n is equal to a product of primes, p1 to the k1 times p2 to the k2 times ... p j to the kj. So it's equal to some product of primes. And if n is less than 1, then n would be equal to the negative of some product of primes, p1 to the k1, p2 to the k2 times ... pj to the kj. And these both hold because of the fundamental theorem of arithmetic. So they both hold by the fundamental theorem of arithmetic above that any integer greater than 1 is a product of primes. So let's observe that n squared then is, well, p1 to the k1 times p2 to the k2 ... pj to the kj squared. If n was a negative value, then it's negative that squared, but the negative would disappear. So n squared is just equal to this. And this is equal to p1 to the k1 times p2 to the k2 dot 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 pj to the kj times itself, p1 to the k1 dot 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 pj to the kj. And by commutativity, we could also write that as p1 to the k1 squared times pj to the kj squared. And that is also, we could say, by commutativity if we wished. And we could say this simplifies to p1 to the 2k1 times p2 to the 2k2 times dot 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 pj to the 2kj. All right, so to some degree, all that simplification isn't totally necessary, but we can observe that a prime pi divides n if and only if the prime pi divides n squared, since the primes in each decomposition are the same. We just have a different number of those primes. So we see that, so the statement is true in this case. Okay, so we could use the fundamental theorem of arithmetic when the absolute value of n was greater than 1. We knew that n would then be the product of primes, or a unique product of primes. Let's do other cases. So let's do another case. This is case 2. If n is equal to 0 or n is equal to 1, then n squared is just equal to n. So the statement clearly holds. Anything that would be true about n squared would also be true about n, and vice versa. And case 3, if n is equal to negative 1, that's the only case we have not looked at so far, then no prime divides negative 1, and no prime divides 1. So since no prime divides n or n squared, and so clearly, again, the statement holds that the same exact primes divide both n and n squared in this case. So we are done. So we've shown that for any integer n, the same primes divide both n and n squared. One thing to observe is that this statement is not true in general for any integer x. So, for example, x divides n squared does not imply that x divides n. Let's see an example of this. If n is equal to 6 and x is equal to 4, then 4 does divide 36, 4 does divide n squared, but 4 does not divide 6. So the theorem above holds when p is a prime, but does not hold in general. Okay, so let's use the theorem above to try to prove the following proposition. If a and b are integers, then a squared minus 4b minus 2 is not equal to 0. So let's try to prove that, and we might somehow use the fact that a prime divides n if and only if a prime divides n squared. So give that a shot, and we'll talk about it in a moment. Okay, so if a and b are integers, then a squared minus 4b minus 2 is not equal to 0. Let's try to do a proof, and let's try to do this by contradiction. So assume for contradiction that, so we want to assume the negation of the statement above. The statement above is an if-then statement, and we know that the negation of a statement P implies Q is P and not Q. So that is what we want to try to assume. So assume for contradiction that A and B are integers and A squared minus 4B minus 2 is equal to 0. So that is what we're assuming. Then we could write that a squared is equal to 4b plus 2. So we could try to get one variable alone by itself. Okay, anything that we notice about 4b plus 2? One thing we could notice is that this is an even integer. This is equal to 2 times 2b plus 1, where 2b plus 1 is in the integers. So that means that 2 divides a squared. It means a is equal to an even number, so 2 divides a squared. Now, by the previous theorem, since 2 is prime and 2 divides a squared, 2 also divides a. And so a is equal to 2k for some integer k. Okay, let's look at our original hypothesis. We assumed a and b were integers and that a squared minus 4b minus 2 is equal to 0. Let's substitute 2k in for a in our original expression, or in our original equation, giving 2k squared minus 4b minus 2 is equal to 0. This would imply that 4k squared minus 4b minus 2 equals 0. And it looks like we might be able to arrive at a contradiction showing that something is both an integer and not an integer. If we're able to do that, we know it's not possible for a number to simultaneously be and not be an integer. So let's try to arrive at that kind of contradiction. So this would imply that 4k squared minus 4b is equal to 2, dividing both sides by 4 gives k squared minus b is equal to 1/2. Since k and b are in the integers, k squared minus b is in the integers, but 1/2 is not in the integers. So 1/2 is not in the integers. This is a contradiction. So we proved that the original statement could not be, so we proved that the negation of the original statement could not be true, and therefore the original statement is true.